Okay, I think we can get started. So welcome everyone to the 2022 edition of the ICTP Spring School on Superstring Theory. For many of you, this will be, or for some of you, this will be actually your first in-person school post-COVID. Before I talk about the school, I want to say just a few words about the ICTP itself, for those of you that don't know it. It was founded in 1964 by a Pakistani physicist, Abdus Salam, who later went on to receive the Nobel Prize in Physics together with Weinberg and Glashow for the construction of what is essentially now known as the standard model of particle physics. It's based on a so-called tripartite agreement between the Italian government, the International Atomic Energy Agency, and UNESCO. Most of the funds for the institute are generously provided by Italy. And the Atomic Energy Agency also contributes a significant amount, whilst UNESCO generously provides the administrative structure within which we operate. The reason for the foundation of the center is that Salam wanted to create a kind of home away from home for scientists who come or reside in developing countries where facilities for research are not as may not be as advanced as in other places, and as such, it has a mission to foster science and mathematics in developing countries. So as a result of that, you can see that we have many different, you can, for example, see on our website, the host of activities and programs that we do. So this school is one of maybe 50 or so activities that take place here in Trieste. We also have significant numbers of activities taking place in developing countries all over the world. We have a close collaboration with other institutions in Trieste, namely CISA, which is the Italian School of Advanced Study, the University of Trieste, University of Udine, which is a city nearby, the INFN, the National Institute for Nuclear Physics, which is actually a co-sponsor of this school, the National Institute for Astrophysics. In fact, there are many, I mean, I've mentioned these institutes that have significant physics and mathematics research activities. Trieste happens to be one of, I mean, a place with arguably one of the highest densities of physicists in the planet. The school itself goes back to the early 80s and has happened every year apart from 1 year due to COVID since 1980, I think 1981, anyway, the early 80s. And as such has become a standard event in the calendar for young theoretical physicists working in particle theory and string theory and related topics. This year's school has been organized by myself, Pavel Putrov, who's another staff member here, and Francesco Benini, who is professor at CISA. And you'll meet both of them as the week goes on. We've got 4 lecture courses happening. 3 of which are in person, with the lectures by Kevin Costello taking place via Zoom at the end of each day. There will be coffee breaks in between. So there are 2 lectures in each morning, 2 each afternoon, with a coffee break in between. I think the coffee will either be outside here or on the terrace level, which is 1 floor up. That's the level on which you also find the cafeteria, where you can have lunch if you want to. 1 floor above that is a bar that has coffee and lighter food and other beverages, should you so need it. This evening we'll have a welcome reception and a poster session. Some of the in-person participants are going to be have printed posters that will be on display, and there'll be an opportunity to discuss with them. And I think that's all I want to say. Pavel, is there anything that I need to add?
Well, maybe you can mention that Friday afternoon there will be this session of celebration of defect.
Oh yeah, so if you look at the program, there's a session celebrating 25 years of the Journal of High Energy Physics, which was founded at CISA. And so there'll be some talks there, but then that event will be followed by a reception, which is in the city of Trieste, and there'll be a bus service. I mean, we're providing a bus that will take anyone that wants to go to that downtown, but you can also take the public bus if you so wish to. So with those introductory remarks out of the way, I'm going to hand it over to Pavel, who's going to chair the first session.
Yes. So for our first opening lecture, we are very happy to have Ethan Monk from NYU, who will tell us about non-invertible symmetries.
All right, can everybody hear me? Okay. Thanks very much for the invitation, and it's my great pleasure to visit ICTP and to open this lecture series. My lectures will be on this topic of non-invertible symmetries. Okay. I should say that during my talk, if you have any questions, please just speak up. Let me start with some motivations of this subject, in case that you're not familiar with this recent mini revolution. So we'll start with some motivations. Okay, as you probably all have learned from physics courses, that symmetry is perhaps arguably the most important organizing guiding principle in dealing with physical problems. Okay. First of all, symmetry is ubiquitous, meaning that even messy system can exhibit symmetry properties at long distance. Second of all, symmetry gives rise to organization principles. For the physical observables, okay? And the examples of that take the form of selection rules, or the usual kind of laws you can derive from charge conservation. And thirdly, symmetry can often give rise to non-trivial constraints dynamics of the quantum systems. Such as constraints on the renormalization group flows in quantum field theory, as well as constraints on the possible IR phase diagram of a given UV description. Okay. And given these nice things about symmetry, it's a very natural step that given a physical system to first identify, therefore, given any physical system, a natural first step to solving that system is to first identify the symmetries of the problem, and then deduce the dynamical consequences. Okay. So now I have said some nice things about symmetry and how we use symmetry to constrain physical systems. Let's review a brief history of symmetry or the success of symmetry. Okay. Emphasize the recent history of symmetries in quantum systems, okay, quantum mechanical models. Okay, so the first list in this historical list is not so recent. It's from the 1930s. Okay, that's where the foundations. That's when the foundations of symmetry in quantum mechanics was laid down by pioneers like Wigner. Okay, in those cases, the symmetry will be associated with a group, which I'll denote by G. Okay. And then the power of symmetry was greatly used in the study of quantum field theories. In that context, the central subject will be these continuous symmetries, such as the spacetime Lorentz symmetries, as well as the electromagnetic symmetry, as well as the gauge symmetries in the context of a center model. Okay, and their power have been used in the context of studying the quantum field theory in the 1980s. Okay, and produced many amazing results. And then shortly after, perhaps not well appreciated at that time, is the discussion of discrete symmetries, which is generalization of these continuous symmetries, which are associated with continuous group, to the case when the group is generally discrete. Started from the paper of Dijkgraaf and Witten around this time. Okay, this was not as much appreciated in the high energy community when it was first put out, but it has spurred active development in condensed matter. In the condensed matter community, in particular condensed matter theory community, because these discrete symmetries naturally show up as symmetries of lattice systems. Okay, and people in the condensed matter community have used the results from Dijkgraaf-Witten to understand phases of these systems that are described by lattices at some cutoff scale. Okay, and this was around 2010s. And then there's the interaction between the high energy community coming from this the first description of this discrete symmetry and anomalies from this paper to the condensed matter community doesn't go one way. There's also a feedback from the condensed matter development for discrete symmetry back into the high energy community. And one prime example is the work of Gautel, Kapustin, Heiberg, and Willett in 2014. Okay, and in this paper, they discuss generalizations of this discrete symmetry, which have received active development in condensed matter theory, and further generalize it one step further. Okay, and in particular, a key result of this paper is this generalized notion of symmetries. Viewed as topological defect operators. Okay, this is a notion that encapsulates or captures all the previous notions of symmetries and allows further generalizations. Okay, and the further generalization comes in two branches, roughly speaking. Okay, so there are many further generalizations since around 2015. One type of generalization is to still insist on having some group associated with the symmetries. This leads to the higher form symmetries. Okay, which is already discussed in the original paper. And this is generalization of the old well-known center symmetry in Yamil's theory. Okay. And another generalization is to still having some notion of group, but consider a higher version or generalization, and this gives rise to the higher group symmetries. Okay, and all these guys have the feature that they're associated to some underlying invertible structure that is characterized by a higher group. In general, a group or a higher group of generalization. And there's steady progress to date to understanding these symmetries in various physical systems and the anomalies associated with symmetries, which can be used to deduce dynamical consequences. But that is not the focus of this talk, of this lecture series. Okay. Meanwhile, around the same time, another branch of development in generalizing symmetries come from generalizing the notion of group to something more drastic. So this also happens around 2017. This gave rise to the notion of non-invertible symmetries. If you look into the literature, these symmetries come with many names. But in this lecture, to avoid any confusion, I'll stick to the name of non-invertible symmetry. But in the literature, you may also see people referring to these symmetries as categorical symmetries, fusion category symmetries, and so on. Okay, or higher category symmetry. The definition of symmetry, which we will discuss in detail in the lecture series, relies on this perspective that treats symmetries as topological defect operators. Okay, so the non-invertible symmetry will be associated with topological defect operators, but will be associated with this general topological defect operators, which are not associated with group. In other words, they're not invertible. Okay. Okay. All these notions will explain in detail in the main parts of lecture. Okay. And why do I say this is a drastic departure from the previous notion of symmetries? That is because from the foundations of symmetry that's laid down by Wigner in 1930s, a crucial assumption made for symmetries is that it should define a unitary operator on your Hilbert space. Okay, but that is closely related to the notion why symmetries discussed in the past are always associated with a group. Okay. A consequence of non-invertibility is that the corresponding symmetry operator, the topological defect operator, will not become a unitary operator acting on Hilbert space. So that's a very drastic departure. Okay. So let me just. So you may have some immediate questions on your mind, okay? Since this is something so drastic, okay? The first question is that even though this is some objects as allowed by this perspective, okay, just insist on topological defect operators, but without associating with two group, do they really exist in interesting quantum field theories? Okay, or is this just a mathematical fantasy? Okay, a generalization that has no physical origin or any, and furthermore, no physical implication. Okay. Yeah. Yeah. So I'll come back to that. Yes. So when I say when I discuss this, I do not mean that the symmetries are new. The symmetries always exist. Okay. It was just not put into this universal framework. And indeed, there are examples which I'll mention shortly. Okay. As is true for any symmetry in quantum field theory, they always exist. They're just waiting for us to discover them. Okay. Okay. And the second question is, if you can you can identify some examples. Do these examples produce new dynamical constraints? Okay. In other words, if they only produce constraints which can be rederived using ordinary symmetries, then it's not very interesting. Okay, so why do we need to develop this new machinery? The key question is, do they produce new dynamical constraints? Okay. And the answer is yes, as you may have imagined. Otherwise, I wouldn't be giving this set of lectures. Okay. So let me now get to some examples of these non-invertible symmetries. And along the way, I'll give some references for which the lectures will be based on, and some additional references for further reading on this subject. Okay. We can think about what I'm going to say as a guide to literature on non-invertible symmetries. So the first development for non-invertible symmetries comes in 2 dimensions, a space-time dimension equal to 2. Okay, as was already pointed out in the audience, there are already examples of these non-invertible symmetries in rational conformal field theories, date all the way back to the work of Valente, 1988, and furthermore, the work of Petkova and Zuber in 2000. Okay, in which case they discuss non-invertible symmetries in rational conformal field theories, such like the Liouville theory, well, such like the rational minimum models. And there are also generalizations in the Liouville theory, okay? Which is not really a RCFT, but it's for certain line operators in that certain topological defect in that case, they can be described. And thanks to work of Valente. And there are huge generalizations of this original work by Frolic, Fox, Runkel, Schwiegert, in the sequence of papers starting around 2006, which essentially fully specified the set of topological defects in RCFT that preserve a Carrel algebra, some symmetry that's beyond the Virasoro symmetry. Okay, we'll get to that notion later, and this will be typically referred to as some kind of a Valente lines or some suitable generalizations when RCFT is defined by a non-diagonal modular invariant. And shortly after this work, okay, for like folks Runkel, Schwiegert, there are also realizations of this non-invertible symmetries or this non-invertible topological defects in lattice model in 2 dimension. Okay, so classical lattice model, statistical lattice model in 2 dimension by the work of Asen, Fong, and Bentley. Okay, a sequence of 2 papers, okay, which spells out concretely at the level of a lattice model this non-invertible symmetries for the special cases like the Ising lattice model. Okay, and there's they also discuss some generalizations to I think parafermion theories. So before, there were always examples in this RCFTs and lattice model related to RCFTs. And what I was saying here, okay, was the recent development that put this previous development into a more general framework. Okay, and that started with the work of this gentleman. And also around 2017, okay? And this puts this discussion of topological defects or non-invertible symmetries in 2-dimensional quantum field theories into a very general axiomatic framework, and consequences for such symmetries for consequence of such symmetries for RG flows in 2 dimensions. What is discussed in many other papers, including this one as well as this one. Some joint work with Ryan Thorgren, okay, as well as this nice paper from Minkowski and company. Okay. And that's the development in 2 dimensions so far. As you can see, this is very recent, very rapid developments from 2017 all the way to 2021 and to date. Okay, dots are unfortunately running out of space, but there are further developments in 2-dimensional in discussion of 2-dimensional invertible symmetries even this year. Okay, and going beyond, now I have discussed the 2-dimension. The natural question is to ask if such non-invertible symmetry also exists in 2 dimension, okay? And the answer is also yes, okay? And there are many exciting work in this case, starting from last year, okay? In particular, this work from Troy, Cordova, Xing, Shao, Lam and Shao, sorry. Okay, which will discuss a version of topological defects which generalize those discussed in these papers to the case of 4-dimensional gauge theories. Okay, in particular, say the Yang-Mills theory with orthogonal gauge group. Okay, and similarly for super Yang-Mills theory, and for super Yang-Mills theory with unitary gauge group. Okay, turns out that such non-invertible symmetries show up in those contexts as well. Okay, and there was also a related paper that appeared around the same time, discussing similar and also different topological symmetries, non-invertible symmetries from topological defects in 4-dimensional theories, as well as in 3-dimensional theories, from the paper from Kaidi, Omori, and Jen. Okay. And in particular, in these papers, they also kind of generalize the results obtained from these papers on constraints from these non-invertible symmetries RG flows to the case of 4-dimensional theories. In particular, they can prove statements like that in the 4-dimensional gauge theory with orthogonal group, for example, where these non-invertible symmetries are present. You can argue that any RG flow preserving this non-invertible symmetry has to end at a non-trivial IR phase. So what I was saying, for non-trivial constraints RG from this instances of non-invertible symmetries. Okay. And in some paper that just appeared, I think a week or two ago, there are further generalization of all the framework that I've already reviewed over here. So there's a question you can ask here already here is that there are two branches of generalizations, which I mentioned. One generalization from this topological operators is considered higher form symmetries and higher group symmetries. We're still invertible. Okay. And another generalization is to talk about this non-invertible symmetries. And you can ask if there's some kind of more general structure that put this together. Okay. And this is some that's work still being developed, but there's already a nice paper on this subject that's started to discussing this general framework from these authors. Appeared a few weeks ago, which discussed this kind of larger framework that's known as higher category version of the non-invertible symmetries. Okay. So that's a brief historical walkthrough for the developments in the field of non-invertible symmetries over the past decade. What is the general lesson that we learned from all these developments? Okay. The first lesson is that, quite on the contrary, before you may expect, because this is such a drastic departure from the usual group symmetries, which is ubiquitous in quantum systems, you may think that these symmetries are exotic and rare. But quite on the contrary, these non-invertible symmetries are also ubiquitous. Okay. So let me give you two kind of intuition for why they're ubiquitous. The first intuition is that almost all known DFTs in D equal to 2 have them. Okay. In fact, the only 2D CFT which I know that does not have a non-invertible symmetry is the SU2 W model at the level 1. Okay. Okay. Second, there's a very nice recent work from Topological and Symmetry. Now, which explains that in dimension bigger than 2, the non-invertible symmetries are as common as non-anomalous higher form symmetries in these theories. Okay, so in other words, if you already accept that the higher form symmetries are interesting objects to study, then we are behooved to also study this non-invertible symmetries, because there's universal constructions, as shown by these authors, that gave rise to non-invertible symmetries by the mechanism of condensation. Okay. Or as these authors put it, higher gauging, which is a way to gauge this non-anomalous higher form symmetry on some hierarchical dimension submanifold outer spacetime to generate non-invertible symmetries in the same theory without changing the theory. Okay, so higher gauging is different from ordinary gauging in the precise sense that it does not change the theory. Okay, but they allow you to recover, to discover that you have these non-invertible symmetries in the same theory. Okay, once you have this non-anomalous higher form symmetries. Okay, and because of that, it has been an active field of research. Okay, and in many efforts on again identifying non-invertible symmetries in quantum field theories, okay, particularly in non-quantum field theories, and deducing the dynamical implications, some of which we will review in these lectures. And moreover, this kind of game is what we played in the context of symmetries, even before we talk about the for the ordinary symmetry, even before we talk about non-invertible symmetries. So it's really running the old game of constraints from symmetries using this new tool, this non-invertible symmetries. Okay, but more crucially, from these exercises, we want to find some universal patterns. Such as a notion of anomaly or this non-invertible symmetry. So anomaly is a very powerful universal pattern that was observed in studying constraints from group-like symmetries on phase diagram of quantum field theories and RG flows. Okay, having a non-trivial anomalies greatly constrains where the RG flow can end. So you want to find similar patterns in the context of non-invertible symmetries that give rise to some generalized notion of anomalies, and there are, as we'll see in this lecture series. Okay, so that is the motivation for these lectures. Let me now give the outline for the rest of these lectures. Okay. First, we'll review this notion of symmetries as this general notion of symmetries as topological defect operators. Okay. Secondly, we'll graduate from this general framework and focus on the case of non-invertible topological defects, which define non-invertible symmetries. And we'll see that the mathematical structure that replaces group in the context of non-invertible symmetries will be a fusion category. This is precise. This is precise in the case of one dimension, and in the higher dimension, it will be some higher category. Okay. Don't worry about this word if you have not heard about the category before. We'll make all these words explicit, and if you want to refer to this as this mathematical objects, you can just refer to them as non-invertible topological defects. That's equally good. And thirdly, we'll discuss. I'll provide for you a toolbox for identifying topological symmetries, to identifying non-invertible topological defects, which give rise to these non-invertible symmetries. Okay, which is essentially the tools that were used in these papers to discover many of the non-invertible symmetries in well-known theories, well-known CFDs, and was further generalized in these papers to identify similar symmetries in higher dimensional theories. Okay, so the tools that I will discuss will apply both to the two-dimensional case, and the suitable generalization will apply to the 3- and 4-dimensional case as well. Okay, and lastly, along the way of the discussions, from time to time, I'll discuss dynamical consequences of the non-invertible symmetry that we identify. Okay, and I should say that given this list of recent development, I think most logical way for me to proceed is to focus on equal to 2 for the generalities. Because this is the case where the axiomatic framework for this non-invertible symmetry is mostly well developed. Okay, so the axiomatic framework for these symmetries are still to be developed higher dimensional case, although there are already hints for some structures. Okay, but to introduce these symmetries in a more concrete setting, I'll focus on d equal to 2. Okay, and I use these examples in d equal to 2-dimensional theories, non-invertible symmetry in 2-dimensional theories, to illustrate the main ideas, the general structures. And hopefully this will provide you with the basic knowledge to follow the recent literature that discuss the higher dimensional cases. Okay, and I think this is the moment I should also emphasize the references I'll be using mostly in these lectures. Will be this paper and this paper. Okay, but the other paper that's included in this historical outline provide other references for further reading into the subject. Okay, and most importantly, what I hope through these lectures is to kind of motivate you to study the symmetries, and hopefully the knowledge that you gain from these lectures will be sufficient for you to start your own adventure in the realm of non-invertible symmetries. Okay. With that, let's jump into the first part. That is to review this notion of symmetries as topological defect operators. So let's start slow and recall what conventional symmetries look like in quantum mechanics from the eyes of Wigner. Okay, conventional symmetries in quantum mechanics. Symmetries in quantum mechanics are defined as transformations of states in the Hilbert space okay, and similarly of operators which define your observables, okay, such that transition amplitudes or probability amplitudes are invariant, meaning that things like this, okay, from two states and operator insertion is invariant under this transformation. Question?
Why should it not be invariant up to an overall phase, up to some?
Oh, because
project?
I'm talking about the amplitudes. Okay, so if you're just acting on the states, then in general, the states is defined physically up to overall phase, and that will be related to something I'll mention next.
Okay, thank you.
But the key is that this phase is universal for the Hilbert space. So when you look at this bracket, it will cancel. Okay, that phase is known as projective phase space. I think we're as a refinement of the original discussion of Wigner. Okay, this is what I'm going to say next. So this is a definition of the symmetries. But Wigner in 1930s axiomatizes in terms of axiomatized the notion of symmetry in terms of certain operators in quantum mechanics. That is, these symmetries, okay, they're equivalent to two notions, two kinds of operators. It could be either associated with a unitary linear operator acting on a Hilbert space, or an anti-unitary and also anti-linear operator on the same Hilbert space. Okay, and the latter case is not important for this lecture. It will be relevant if you include, say, time reversal symmetries. Okay, and because symmetries, thanks to Wigner, is associated with these unitary operators, okay, focus on the case without time reversal activated, okay, associated with unitary operators, naturally there's a notion of group, okay. Okay. In particular, this unitary operator, let me call them UG, okay, where G is element of the group. Okay, and the group law is realized by the product of these unitary operators acting on the Hilbert space. Is this part visible to? Okay. Is it visible? For G and G prime inside the group, and this is just the group multiplication law for these group elements. And these unitaries acting on the Hilbert space, okay, or states in the Hilbert space, in general, as follows, okay, and acting on operators by conjugation. Okay. And the related to the question that was asked before, the representation of the symmetry operators acting on, sorry, the symmetry operators acting on Hilbert space in general does not form a representation for this group linear representation for this the group law, but instead a projective representation that is related to the phase ambiguity associated with the states in the Hilbert space. Okay. So far, we're just talking about general quantum mechanics. We haven't used any fact about locality, something that's crucial to the quantum field theory. Okay. Let's move on to quantum field theory. In this case, we have the Noether theorem. The constraints, while the structure of the symmetry is more stringent, in particular, the Noether's theorem implies that if you have a continuous symmetry, say a U1 symmetry, which is a charge symmetry associated with the electron, for example, it will imply the existence of a special operator in your quantum field theory, namely a Noether current, which is conserved. Okay. And the unitary operator that Wigner introduced that applies for general quantum mechanics can be reconstructed from this conserved current. In fact, there's something even more elementary you can define. That is the notion of a charge. Okay, so for example, for the U1 case, a U1 symmetry of an electron, and this will be measuring the charge associated with the electron. And they can be defined as follows. It's an integral over the spatial direction at a constant time of the zeros component of this current. Okay. So it measures the charge of a state that is specified in your quantum field theory by quantizing the theory on the constant time slice. Okay. And this object is T independent. Okay. As a consequence, as the conservation law. Okay. And in terms of this charge operator, Wigner's unitary is just given by the exponential of these charges. Okay. Where the group element, in this case, is determined by the symmetry transformation parameter alpha in this way. Okay. So that alpha can be thought of as a Lie algebra, in this case trivially, for the U1 associated with the symmetry group. Wigner's unitary action operators. Okay, so similarly in the quantum field theory, the symmetry action on operators is also captured by these charges and the unitaries. Okay, in particular, acting on local operators, the symmetry variation acting on local operators at insertion X is determined by the equal time computation of the symmetry charge Q with this operator insertion. Okay, so we saw that in the quantum field theory framework, at least for continuous symmetry, we can recover all the ingredients that Wigner introduced for quantum mechanics, but we have something more. We have this local object, this conserved current, and then we can define these charges. Okay. We can go one step further, right? Focusing on the case when the quantum field theory is relativistic. Okay. Which is equivalent after weak rotation to a Euclidean quantum field theory with, in particular, rotation symmetry. In which case, you are free to orient your choice of constant time slice. Okay, you can free to choose your direction of time, and consequently, there's a generalized notion of the charge operator. Associated with a general, not necessarily a constant time slice, but a general codimension 1 manifold in your space-time, denoted by sigma upper d minus 1. Of the Hodge dual of the current 1 form, So here the current one form is defined as follows. Okay. And the Hodge dual satisfy the Hodge dual give you a d-1 form. That's why you can integrate over this d-1 dimensional submanifold. And the current conservation is equivalent to the closeness condition for this Hodge dual for this d-1 form. Okay, this is from conservation. Okay. And similarly, the unitary is given by the exponential of this charge operator as before. Okay. And the way these operators, this charge and unitary operators act on your local operators is by enclosing it. Okay. So for example, if you have a local operator over here with subscript q, which will define its charges under this U1 symmetry, focus on the case, to be explicit, focus on the case when the symmetry is a U1. Okay. Enclosing it by the charge operator, okay. For example, taken to be a sphere of d-1. Intuitively, this will measure the charge that's associated with this operator, okay, sourced by this operator. Similarly, if you encircle the same operator by the corresponding unitary, okay, this will implement the symmetry transformation on the corresponding operator. Okay, so in other words, you can shrink this ball and replace the left-hand side by the symmetry transformed operator. Now, a crucial property of these integrals, the charge operator defined this way and the unitary operator defined this way, is that they are topological, meaning that even though in these pictures I've drawn such that the encircling codimensional manifold is a sphere, it doesn't really depend on the metric on the sphere or the shape of the sphere. It only depends on the topology. Okay. And that is a consequence of this being a closed d-1 form. Okay. And consequently, that this kind of integral only depends on the topology of this of the manifold integrating over as a consequence of the Stokes theorem. Okay. So what's the implication of this topological property? So this object, okay, this unitary defines the prototypical example of a topological defect operator. Okay, the notion of topological is what I have just explained. Why it's called a defect is because it has a dependence, even though topologically on the higher dimensional manifold. It's not inserted at a line, inserted at a point, but it's wrapping some higher dimensional submanifold. Okay, as opposed to a point. That's why it's called a defect. Okay. The fact that it's topological is closely related to constraints and correlation functions in the following way. So imagine some general correlation function that you're studying in the quantum field theory, okay, with various insertions. Okay, and potentially symmetry topological defect operator, which I'll call UG, inserted somewhere in this correlation function. Okay, and suppose that in the neighborhood of this topological defect, we have an operator insertion which we make it explicit and call it phi. Okay. The fact that this object is topological means that if we focus on this region, let me draw it over here, save some space. we are free to deform the locus of the symmetry defect or the topological defect operator, okay, keeping the location of insertion fixed. For example, we can deform it all the way to something like this, okay? And this equality means that we are free to replace this configuration locally by this configuration without changing the correlation function. Okay. This is called isotopic invariance. Okay. Furthermore, if you have more than one topological defect operator inserted in your correlation function, there's the fusion, okay, which is the characterization of the group multiplication associated with the unitary operator that Wigner defined in the context of the quantum field theory. Okay. In this case, just to be concrete, you can think about the diagrams I'm drawing is the projection of the higher dimensional diagram down to 2 dimensions. And if you're not comfortable with that, just focus on the case when spacetime is 2-dimensional. Okay. So the codimension 1 manifold, the sigma is always just lines or circles. Okay. In the presence of 2 such topological symmetry defects, topological defect operators, they all mean the same thing. If there's nothing inserted in between, because they're topological, you can zoom far away, okay, and they look like a single defect insertion, which is labeled by the product of the individual group element enters here. Sorry, the same sigma. Okay. So I'm taking the limit where they collide, and in which case the same sigma, and given by this. Okay. Right. So right. So the orientation is related to how I label this defect by group elements. In particular, if they are not oriented, if they're oriented in the opposite way, like this, this will be equal to the trivial line, meaning that there's no insertion. The reason is that so this is the with the bar, okay, denoting the opposite orientation. The reason is that you can connect the 2 ends of the line, in which case you just form a circle with no insertion. And that will be the case that you are detecting the charge of the identity or the charge of the vacuum, and that's trivial. Okay. So that this is how the 2 orientations are related. Okay. Now, once we understand fusion, we can go 1 step further in this picture. Okay. So recall the usual way you determine what are entities is to reduce the insertion of the substance, reduce the insertion reduce the correlation function with the insertion of these unitaries to something that depends on the charges of the insertions. Okay, and then you can deduce consequences such as the charges of insertions have to add up to 0 for this correlation function to be non-trivial. And to do that step, you want to be able to move across this topological symmetry defect away from this insertion. And there's 1 step involved, which comes from doing a fusion of the 2 ends of this topological line. Okay, and that's equivalent to doing this, okay, locally. And as a consequence, what you find is something like this. Okay, and this generally is equal for a general group, for a symmetry defect associated with general group, as the transform operator in the presence of a line which have been moved across the operator insertion. Okay, and this feature, the fact that there's a simple way to move the symmetry line across the local operator insertion with no other line attached, is actually a feature of this invertible symmetries, and we'll see how this generalizes in the case of non-invertible symmetries. How many minutes do I have? We started late, right? Okay. All right. I'm ready to summarize this part of the discussion, this review on symmetries as topological defects. Okay. So some comments. Okay. The first comment is that the isotopy invariance, okay, meaning that the deformation of an observable in the presence of this topological defect operators is invariant under small deformation of the line as long as they do not, do not cross other operator insertions. Together with fusion, which tells you how you can further move the line across the local operator, okay, and with the information of how, defects act on local operators. Okay, there are 3 ingredients. The 3 ingredients completely characterize the conventional symmetries as topological defects. The topological defect operators, I'll use them interchangeably. For continuous symmetry, because the presence of the current, which is something more fundamental, this looks like a complicated machine to produce something that's well known. Okay, so why is this useful? This viewpoint of topologicals of symmetries as topological defect is useful already in the context of invertible symmetries when the corresponding group is discrete. Okay, in which case there's no Noether current, and this topological operators, the topological defects, should be treated as rather than as the fundamental objects. In particular, you can, just like in ordinary continuous group symmetries, you can gauge the symmetry by coupling theory to a non-trivial gauge background by turning on gauge connections. In this case, the topological defects give you a natural way to couple the theory to a discrete symmetry background. Okay, let's focus on the case of t equal to 2, just so that I can draw explicit pictures. In which case, the topological defects labeled by G, okay, it specifies the transition function. So a discrete gauge field, a discrete G background is essentially just determined by specifying transition functions, okay, from patch to patch. So you can triangulate your spacetime, and the background is specified by transition functions from different patch, like from the left to right. In particular, the transition function, for example, in this picture, will be given by this G element labeling the topological defect. And furthermore, if you take 2 topological defects, okay, instead of doing this fusion complete together, because they're topological, you can imagine fusing just one ends of the defect. And this gave rise to, and you do not break the topological property through the way, and this will define for you some topological junction. Okay, everything is topological, and together they allow you to form a general network and this is equivalent to a general discrete symmetry background. Okay, so you can think about this as a patch of the full network that you tile on your spacetime. So here, this is topological because in all these junctions, you are using these basic building blocks. And the very nice thing about coupling a theory with a certain symmetry to the gauge field background is because it's a very nice thing because this is a useful way to detect anomalies associated with this symmetry, more precisely the 't Hooft anomaly associated with symmetry. Okay, so it's not a sickness of the original theory with this global symmetry, but it's a feature, and this can be detected by gauge non-invariance once you couple the theory to background gauge fields. In this case, in the discrete case, this topological defects. Okay. Detected by change in the network topology. Okay. So the basic ingredients I was talking about here, isotopy invariance and stuff like that, it ensures that topological network is invariant under small deformations of all these vertices, okay, as long as they don't cross each other. Okay. But if you focus on a patch of this diagram, for example, over here, okay, okay. There's a way to change the connectivity of this diagram by performing a gauge transformation, for example, in this region. By doing a gauge transformation associated with, say, G1. Okay. And by doing that gauge transformation, you go to another diagram that with a different connectivity. Okay. Going this way. Okay. So all these internal legs are unambiguous because of the topological vertex condition. Okay. The third leg is always determined by the labeling of the other two legs. Okay. Doing this gauge transformation essentially removes this line, but reconnects G1 with G2. Okay. Reconnects the topological defect labeled by G1 to G2, giving rise to this diagram. And if there's no phase associated with this gauge transformation, that's equivalent to saying there's no anomaly. Okay, so once again, anomaly is diagnosed by coupling the theory to the symmetry background, meaning a gauge field background for that symmetry. In this case, network of topological defects. And if there's a phase coming from doing a gauge transformation, okay, then that signals anomaly. In this case, it's equivalent to changing the topology of the network. And this phase is generally denoted as this, okay? And this, as we're saying, encodes anomalies. Okay? And this phase is not arbitrary, just like usual anomalies are subject to West-Lumino consistency conditions. Similarly, this anomalous phase are also subject to a finite version of the West-Lumino consistency condition. West-Lumino consistency. Okay. And this leads to the constraint that this phase is something classified by the group cohomology H3G with U1 coefficient. Okay. The cocycle condition is coming from the consistency condition, and the fact that you are quotienting out by exact cocycles is related to that. The fact that at these vertices there's some choice of gauge, there's some gauge freedom, okay, and that gauge freedom can allow you to remove part of the phases. But the part of the phase which cannot be removed by this ambiguities over here, which are related to local counter terms in the context of continuous symmetries, is precisely this anomaly, okay. And that's captured by this non-trivial cohomology classes. Okay, and you will see generalizations of this for non-invertible symmetries in the later lectures. Okay, let me end here.
Okay, let's thank Yifan for the lecture. And now we can move to our discussion session where you can ask questions.
This is for me.
It's notepads or pens, so you can take them here. Okay, let us resume. Okay, for our second lecture, we are happy to have Laura Donay, and she will tell us about celestial amplitudes.
Thank you very much. Can you hear me? I hope the microphone works well enough so that you can hear me at the back. No, it's not working well. I didn't touch it. I think it's working, but it's just maybe not close enough.
Yes, it's working.
It's okay? Matteo, I mean, but I should speak louder maybe? Okay, so, so the microphone is for online and okay. If you can put the volume of the microphone higher, the better, so that I don't have to shout. But okay. Well, let's see if you can hear me. I will try to speak out. So thank you very much. It's a great pleasure for me to be here and to see you all here, and also hello people online. So I will be telling you about celestial amplitudes. So celestial amplitude, I will present them as the observables of quantum gravity in flat spacetimes, which live on the conformal sphere at the boundary of flat spacetime, which is called the celestial sphere. And celestial amplitudes are the root of a recent program, which is called celestial holography, and which has been developing very fast in the recent years. So so the goals of this program is to address to which extent we can generalize the holographic paradigm to spacetimes which are more realistic, namely, in this case, which are asymptotically flat. So celestial holography proposes a holographic approach to quantum gravity in asymptotically flat spacetime. And I will define what I mean by that. And so it's a very precise proposal, actually, which is rooted on this celestial amplitude. So celestial amplitudes in this context will play the role of the observables. So they will be actually scattering elements, but written in a convenient way, such as to exhibit the manifest conformal transformation law under the action of the Lorentz group. So they will be the observables of quantum gravity. And they will be living on the celestial sphere. Now we'll recall what is the celestial sphere and what is an asymptotically flat spacetime. So this story and this program is actually now pretty old, and it builds up on many observations that have been made in the last years. Basically, the main observation is that the infrared structure of gravity in flat spacetimes is much richer, more subtle, and also much less understood that we thought it was. And it has to do with some kind of very deep realization that several aspects of physics in flat spacetime are actually deeply connected to each other. For instance, we will see that the so-called asymptotic symmetries of general relativity can give a symmetry principle for very known theorem in quantum field theory, which are Weinberg's of theorems. This is just to mention one of the relation that we will go into more details. And so it's a quite a long story which builds upon physics that belong to different topics. But I think that that is what is very interesting to actually relate all these things together. And of course, so the main goal of this formulation of celestial amplitude has to do with attacking this problem of addressing a holography in spacetime which is not anti-de Sitter, but instead describe in a more realistic way the kind of spacetime we live in. So the motivation for this program, basically the first is to understand the holographic paradigm for more realistic kind of spacetimes. So in particular, I mean, we know that the holographic correspondence has given us this in its most concrete realization is the ADS anti-de Sitter conformal field theory correspondence, which establishes that quantum gravity in a spacetime of anti-de Sitter, so with negative cosmological constant, can be equivalently described by a theory without gravity, a conformal field theory that lives at the boundary of the spacetime. So this paradigm has been proven to be extremely powerful, and we would like to know how we can approach this problem for more realistic spacetime, namely for flat spacetimes which have vanishing cosmological constant. So of course, we know that we live in a universe with a positive cosmological constant, but the approximation of looking at flat spacetime, vanishing lambda, is a very good approximation for a huge amount of physical applications, from collider physics to astrophysical physics, up to scales which are, of course, smaller than cosmological scales. So we know very well how the holographic correspondence works in DDS, but for flat spacetime, somehow the problem is much less understood, and it has to do with several features that are actually inherent to flat spacetimes. The fact, for instance, that the boundary of flat space is not a time-like Lorentzian boundary, but instead a null boundary, where there is no natural notion of locality or time evolution. So this presents new challenges that one is not encountered to face in ADS-CFT. But I don't think that nobody thinks that holography is just a peculiarity of this kind of spacetime, but that is instead a very rich and broad, principle for gravity. So we'd better understand to which extent and what we can make for more realistic kind of spacetimes. So that's the first motivation, is holography basically is nice. The second one, independently of holographic motivations, I think this program of celestial amplitude and celestial holography is very interesting because it unveils new and deep connection between several subfields in physics, as I have already mentioned. So to mention just a few of these topics, and this is what we will start with today, is the topic of asymptotic symmetries, which is a purely general relativity classical topics in physics, in general relativity, GR. We will also deal with quantum field theory, especially sub-theorems that were discovered in the 60s by Weinberg and others. It also has to do with more pragmatic topics, as it actually all this story is beautifully connected to observables in gravitational wave physics. And these are the so-called memory effects. So I will not have time to talk much about memory effects, but roughly speaking, these effects are, if you want, the physical consequences of the fact that we have an infinite amount of symmetries at the boundary of flat spacetimes. And then, as we will see, celestial amplitudes, since we want to relay this to holographic techniques, we will have to also build some connection with the 2D conformal field theories. So this is for the motivation. So let me define maybe a little bit more concretely what we'll do here and what is celestial holography. So this will be a duality. So it's yet to be established between gravitational scattering in 4 dimensions. So I will be working in 4-dimensional asymptotically flat spacetimes. And a yet to be fully understood dual theory, which will be a 2-dimensional theory, which I will refer to as a celestial conformal field theory or celestial CFT. Sometimes I will denote this by CCFT. So what is a celestial CFT? Well, I don't know, but we will go along this path together, and we will see that a celestial 2D CFT shares many features with a conventional conformal field theory in 2 dimensions, but also, as we will see, very different properties and puzzling aspects, which have to do with the fact that we are in flat spacetimes. And people now, it's a rich program which involves many people coming from many different subfields, from scattering amplitudes, from GR, and also people coming from the CFT background. And all these people are really actively trying to come with a better understanding of what is a celestial CFT, what are the constraints of this theory, what are the list of properties that it should obey, and how it encodes gravity in flat spacetimes. So most concretely, what will we do? What we'll do is, what is a celestial amplitude? Is a scattering amplitude, but written in a convenient basis, in which exhibit manifestly SL2C. Invariance, I will explain this all in detail, but just so that you have an idea. So we will describe the 4-dimensional scattering process. So this is the duality proposal. In terms of a very different thing, which is a correlation function in this so-called celestial conformal field theory. CFT2. So if you want, it's a 4D bulk 2D kind of duality, and I will explain why this is an interesting and somehow natural playground for holography in flat spacetime. So now on the left-hand side, I have scattering elements in 4D bulk. On the right-hand side, I have correlation functions, which involve a bunch of operators living on the celestial sphere. And these operators will be labeled by these quantum numbers, a conformal dimension delta, and a 2-dimension and a 2D spin J. So I will explain you how this holographic map works in the third chapter of the lecture. But roughly speaking, what we will do is that, so I will consider mostly massless scattering of massless particles. And massless particle can be labeled by a null momenta, which involves the energy omega. And what we will do is we will trade this energy for this conformal dimension delta via a precise integral transform, which is called a Mellin transform. And the 2D spin, on the other hand, will be simply identified with the 4D helicity of the particle. Let's call it L. So this will just be identified. So we will trade the energy of the particle for this conformal dimension delta. The spin of the correlator of the operators will be the helicity of the particle, and the Z and Z bar will label how the particle enter and exit the celestial sphere. So I will explain this in way more details, but it's just for you to have a broad outlook of what we are going to deal with. So why is it a good thing to do, and what is the new, let's say the new, because there have been several attempts before to get some flat space holography from ADS CFT, and something did work, but most of the things didn't. And the new take of this program is to actually use the huge amount of symmetries that are the Bondi flat spacetimes, which are the so-called BMS symmetries that I will review today. So basically, the new powerful tool that we will use, as we saw in the first lecture, symmetries are extremely powerful, as they will strongly constrain the problem and give an infinite amount of conservation laws in flat spacetime. And actually, now people are slowly understanding that they are much richer and also more subtle than expected. And the goal is to use, to a full extent, all these symmetries to constrain at maximum this problem and the celestial CFT. actually we have an infinite amount. We have infinite amount of infinite towers of symmetries. And these provide for us powerful constraints. And I will explain precisely how these constraints manifest themselves for conformal fit theorists. Is there any question on the motivation? Yes. Yes. Yes, so it's a, yeah, right. So it's different from the usual codimension one type of holography where we have the CFT living in one dimension lore. And this is one of the, if you want, unconventional aspect of that. And I will try to explain where actually, so it always has to do with what is the natural place for the dual theory to live in, right? And actually you could come with a different type of holography. This is something actually I'm interested into, but roughly speaking, we will see that the celestial sphere, which is the conformal sphere at the boundary, which is two-dimensional, because of the nature of the scattering process in flat spacetime, will be naturally playing the role of this holographic screen. It just has to do the fact, in 2 words, with the fact that the Lorentz group in flat spacetime acts as the conformal group on the celestial sphere. So if you recast these amplitudes on the celestial sphere by construction, by symmetry construction, these will naturally transform covariantly under SL2C. So you have the conformal group, and then you can wonder how to extend it to the local group and have a fully fledged 2D CFT. I will come, of course, to that. But indeed, that's a different kind of holography. It's a codimension 2 type.
If 4D has 3 space dimensions in one time, the CFT is just space.
Yes, yes. It will be labeled by this angle Z and Z bar. So it's Euclidean, if you want.
Okay.
Yeah. So we'll see exactly how we start from massless unshelled particle, and then how we can extract the data that they imprint on this 2D sphere.
Thank you.
Another question?
Just a quick question. So is the celestial CFT related in any way from a limit of the ADS CFT in 4 dimension?
From a flat limit?
Yeah, so consider ADS4 CFT3. Is the celestial CFT related in any way by a limit in that ADS4 setup? So
as of now, there is no flat limit process that is giving you the celestial CFT from a flat space limit or large radius limit.
But we know, for example, the S matrix from flat space can be recovered, like in the interior of ADS where the curvature can be neglected.
Yeah, so this is a very interesting thing to look at, specifically what we can have, which kind of relationship we can have, starting from even correlation function in ADS or relating to the one in the celestial sphere story. Some people have started to look at this, but this is something that is not fully understood. And there are actually many reasons why this part is complicated, because actually I think that my take on that is that to have a chance that this works, you have to really strongly somehow relax some of the assumptions that we usually do in ADS CFT. And one of them is the so-called boundary condition and the boundary which are bouncing. Here we will have to allow for outcoming flux. I will come to that when we'll talk about BMS symmetries, but we have to allow for way more relaxed boundary condition in ADS to be able to do this map properly.
Thank you.
Yeah, you said that flat space-time is a good approximation for our universe in some regimes.
Mhm.
But the conformal boundary between positive cosmological constant and zero cosmological constant is non-trivially different. So
Yes, that's a very good point. That's a very good point. And indeed, if I once I will tell you what I can what I know about this, it's far from obvious how it can tell us about DS CFT correspondence. So this is another actually interplay that we might be able to come at with at some point, because indeed the zero spacetime is also very peculiar. But actually there are very reminiscent. We will see there are very reminiscent feature of funky things that happen in the zither also appear in celestial holography. So there are some stuff in common. There's another question there. I will start writing and don't take it bad, but it's just.
Would this CFT live in the asymptotic infinity? In what sense? In the sense that does it live on the spatial infinity I0 or on some fixed slice of scry plus or scry minus?
Yeah, it will live on the celestial sphere. And now I will precisely explain what are all these locations you are talking about: spatial infinity, the non-infinity, the celestial sphere. And this will be clear.
Okay. Thank you.
Thank you. Thanks for the question. If there is anything else, let me know. Also, if you have a question online, let me know. So 2.1, well, let's start with recalling all this, the structure of flat spacetime, and in particular, what is an asymptotically flat spacetime. So I'm supposed to stop at 12:45, right?
Yes.
Okay. So let's start with something you all know, which is exactly flat spacetime, namely the Minkowski metric in 4 dimensions. Have a t, the time coordinate, the radial coordinates, and the sphere angles. Let's take for the moment theta and phi. So this is just Minkowski. Now I will be using a lot in this lecture a new time coordinate. Let me write all this. Let me keep some retarded time coordinate. U, which is simply the difference of t minus r. And very importantly, I will be also using complex stereographic coordinates instead of this theta and phi angle, which are the z and z bar coordinate, which will pop up a lot in these lectures. So they can be obtained by taking e to the I phi cotangent of theta over 2. And z bar is the complex conjugate of z. So it's e to the minus I phi cotangent theta over 2. So in these maybe somehow unusual coordinates, the Minkowski line element just take this following form: minus du square minus 2 du dr plus 2r squared. This gamma z bar thing here, dz bar, where gamma z bar is just the unit sphere metric here, but now written in complex coordinates: 2 over 1 plus z bar squared. So this is just the unit sphere metric. And now let me draw a very important diagram, which is a Penrose diagram for Minkowski space. So Penrose diagram is bringing the infinities of a spacetime to a finite distance And an important thing about this diagram is that light rays and massless particles always propagate along lines of 45 degrees. So time is, sorry, this time here, R. So this is the trajectory of a massless particle in this diagram. So a massless particle follows a null geodesic, and basically, let me draw here. So what is a bit weird is like constant R curves in these spacetimes are like that. So these are constant radial coordinates curves, and constant time slices are here in blue. So these are t equal constant in this diagram. So I'm not recalling how you make the change of coordinates to how you make the conformal compactification. By the way, you can, a good reference for this lecture is Strominger lecture notes, which are on archive. So in this diagram, the null coordinates u is going in this way. Very good. And so actually each point of this diagram is actually a two-dimensional sphere. Well, it's not exactly, it's a half a sphere which is mapped to the other side, but let me be a bit sketchy, and you can ask more about that after if you're interested. But basically each point in this diagram is a two-sphere, which is labeled by this angle Z and Z bar. Very good. So there are different locations in this diagram. So one I was just asked is this place is called spatial infinity, I0. Spatial infinity is the place you reach when you take R going to infinity and T constant. You have past time like infinity and future time like infinity. I will not talk much about that, but basically, this is the location where massive particle end their life. So a massive particle will have this kind of trajectory in flat space, and it ends its life here at I plus, which is future time like infinity. So which is obtained when you take T infinity. But since I will be dealing mostly with massless scattering of massless particles, I will be especially interested in this null hypersurface here, which is a null hypersurface, which is called future null infinity. And denoted by this letter calligraphic I scry plus. This is scry plus because this is the future, but there is a past analogous of this hypersurface, scry minus, which is past null infinity. I hope you can read something on this diagram. If something is not clear, just let me know. Good, so what is the celestial sphere and where will our theory be living? So let me erase this Minkowski line element. So as I said, each point in this diagram is a two-sphere. And so topologically, future null infinity is a real line, which is spanned by this coordinates u times the two sphere. And this sphere is called the celestial sphere. Yeah, I write this CS2. Maybe sometimes I will write this CS. Yeah, let's keep it like that. I don't promise I will be consistent all the way through, but so it's really the sphere that you can see when you look at the night sky, approximating that we live in flat spacetimes, but this is nothing but the celestial sphere is just the sphere you can see at night. So that's flat spacetimes, and this is the conformal compactified version of this flat spacetime with this Penrose diagram. So the important thing about that I want you to focus on is that massless particles propagate along 45 degrees and end their life here on this null hypersurface, which is called future null infinity. And the massless particle also come from another location, which is the past null infinity. So there are different ways to draw this diagram. Sometimes people draw the version which is a triangle, but I found this one is less confusing. So this is just Minkowski. Now we'll be interested in more generic kind of spacetimes, which are the so-called asymptotically flat spacetimes. So roughly speaking, an asymptotically flat spacetime is, as you might guess, a spacetime that looks like Minkowski seen from very far away. And this is indeed what it is. But there is a precise definition of what we mean by looking like Minkowski from far away. And this definition is given us by the seminal work of Bondi, van der Berg, Metzner. Van der Berg is always dropped for some reason. Let's put it back for once. Van der Berg. Namely BMS. So these guys, they make a very important piece of work in the 60s. So these guys are general relativity people. And at that time, it was not very clear whether gravitational waves in GR actually also actually existed. And they wanted to make some work that were to prove the existence of gravitational waves at nonlinear level. And this led them to define this so-called asymptotic flat spacetime. So what is that? Well, in the first approximation, this is a flat spacetime. So it will be given by the Minkowski line element that I have written before. This is just Minkowski, plus some correction, which will be tamed away as R is very big. So this will be a large radius expansion. And there is a precise prescription for this. And this will be important. So we are doing a large R perturbation of flat spacetime. I'm writing some stuff in green and in red, and then I will explain what these are. What I can already tell you before I forget is that this big D capital, well, with an index Z of Z bar, is the covariant derivative with respect to the sphere metric, so gamma z z bar, which raises and lowers z and z bar indices. And also sometimes you will catch me using this notation, big A, just to denote collectively the angles z and z bar. So we have a few terms here, but remarkably not so many. Not so many terms that we need to add. And this will be good enough for these lectures. So I have dz of E, z, z, c, z, z. So I'm writing here just one holomorphic component, but I have the complex conjugate. So this CC means complex conjugate, where everything I've written is copied, but putting z bar instead of z. And then we have plus dot dot dot. Plus dot 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 meaning some subleading corrections in this 1/r expansions. Okay. So what is that? And what are these functions in green and in red? So let me explain that, and then you can ask me some questions. So this function M here is called the Bondi mass aspect. And this NZ here, there is also an NZ bar, is called the angular momentum aspect. So what are these? Well, roughly speaking, as their name suggests, M just encodes the total energy of the system you're describing, and Z has to do with the angular momentum of the thing you're describing. So if you take a Kerr metric, just a Kerr metric black hole solution, you write this into these coordinates, you will see that this M here is just nothing but the mass of the black hole. So in this case, it's just a constant, but here I'm allowing for more generic kind of spacetimes because I'm allowing this function to depend arbitrarily on the retarded time and the angles. And the angular momentum aspect will be, of course, related to the angular momentum of the Kerr black hole, if you were to expand this solution into these coordinates. But you see, I'm considering a much more generic kind of setup, which is this BMS asymptotically flat spacetime. And this function here in red is the asymptotic shear of null geodesic congruence, asymptotic shear for short. And it's very important because its present is telling you whether the system you are describing is emitting gravitational waves. So in particular, if you define this, so here I'm using AB as collectively for Z and Z bar. This object, which is the retarded time derivative of the shear, is called the News tensor. And so it encodes the presence of outgoing radiation. So this is very important. Now, why have I written this in red and why this in green? Well, the difference between these two things is that Einstein's equation implies some evolution equation or constraint equation on the Bondi mass and the angular momentum aspect. So roughly speaking, if you solve Einstein's equation, order by order in R, you will see that the time derivative of M is constrained to be something. And similarly for N, Z, and Z bar. On the other hand, this CAB here is not constrained, so it's really a free data that you put in the theory. So it's qualitatively different than the other two things. And so basically, roughly speaking, it encodes the two polarization modes of the strain measured by a gravitational wave detector at very large distance. And just then I will stop writing thing and I will take questions, but just to explain a little bit more physically what this metric mean. So there is this very famous formula which is called the Bondi formula, but actually it was also found by Trotman. I heard recently a bit before Bondi. There is this very important formula which is explaining a little bit what's going on here. So it's telling you basically that the integrated version on the sphere of the mass aspect decreases in time. And the reason why it's decreasing in time, it's because there is gravitational waves which is escaping the system. So it's very easy to understand. You have some gravitational system which is emitting gravitational waves. The wave is escaping through null infinity, and as a consequence, the energy decreases. So this formula was the first, actually, theoretical evidence for the existence of gravitational waves at non-linear level. Is there any question on this diagram on the definition of asymptotic flatness or on these functions? Yes.
Yeah, just a trivial notational question. So just to be sure. So CAB, the non-zero components are just CZZ and CZZ, C bar, CZ bar, Z bar. There's no CZ, Z bar component.
It's symmetric and traceless. Yeah, yeah.
Okay.
So indeed, we'll have CZZ or and CZ bar, Z bar. So yeah. So these are the encodes the two polarization degrees of freedom, basically.
So why there is no energy coming in from the past? You only have
yes,
energy
there
going
is. I am sorry. They can be ingoing. So everything I'm writing can be also written for incoming incoming waves. So in this case, thank you for the question. So in this case, we will use a different set of coordinates. We'll use an advanced coordinate V, which is now T plus R, which is running here along this now past null infinity. And everything I have written can be repeated for incoming wave in terms of these advanced coordinates. So here I'm really doing all the analysis at one boundary. And we will see later how actually, when we will want to talk about the scattering problem, how the data, the past and the future are related to each other. But it is, I'm focusing on outgoing gravitational waves for just the sake of, you could repeat everything in advance. And in the lecture note of Andy, you can find the relevant formulas.
Hi.
Yes.
is there any specific conditions on Riemann tensor that asymptotic flatness, this asymptotically flat spacetime should follow? Like, what are the conditions on Riemann tensor for?
So we'll just say that it's flat, basically. That you can solve the Einstein's equation, and you will see that.
No, but after Einstein equations, there will be some conditions coming from this Riemann tensor, right? So, there's this electric components or magnetic components of sorry, Weil tensor. I meant Weil tensor. So
okay.
So what are some specific conditions on
yes,
Weil tensor?
so basically here, this expansion, the fact that I am making an expansion in R, in a Taylor expansion in R. And you see, for instance, I didn't include log of R. I could have put some log of R in principle, but basically this expansion is in, I will not say one-to-one because there might be some subtlety arising, but basically is almost equivalent to the peeling theorem in GR, so which is telling you that the Weil tensor has certain precise fall-off in 1 over R. So these things satisfy peeling theorem. Now, if you talk to a mathematical GR guy, they will tell you, yeah, but we know there are solutions that do not satisfy peeling and so on and so forth. But and this is a good comment. But here, basically, as you see, I'm assuming there is a conformal compactification holding and all this. But this is good enough and actually very excellent for what we want to discuss. So there are precise fall-off on the Weil. All right. Am I allowed to use time of the discussion? No, I'm not allowed. Okay, then I will have to tell you what are BMS symmetries in the few minutes remaining. But now we have introduced most of the things we will need. And sorry for the GR detour to amplitudes, but if we don't do that, we will not understand where this theory is living, what are these coordinates, and where the constraint on the celestial CFT come from. So let's go to BMS symmetries. So what we want to look for, so we want to answer the question, what is the symmetry group of asymptotically flat spacetime? The symmetry group of flat spacetime, we know is Poincaré. But now we are looking at a bigger, or if you want, more relaxed kind of version of flat spacetimes. And it's not clear what are the symmetries that would preserve such an expansion. So what we want to look for, we will look for infinitesimal vector fields of this type. These I'm just writing down all components because I'm nice. So we want to look for these kind of vector fields which preserve these asymptotic expansion. So this is the Lie derivative along psi of the metric. And we will ask this not to be exactly 0. That would be looking for a killing vector. We don't want that. We want something that preserve the asymptotic structure. So we want to ask two things. So the two rules of the game we want to play is we want to preserve the fall-off conditions and the gauge fixing. I didn't talk about the gauge fixing. There are some, it's actually important. There's some gauge fixing in the metric, but if you're interested in that, you can ask me. But so this is what we cannot do, is to mess up with these powers of R here. We don't want to introduce the R to the 2 here or something like that. We want to keep the expansion like that. But what we can do is we can change this function in green and blue and red. So we can change the Bondi mass, the angular momentum aspect, and the shear. This we can do. And when you follow this game, what you find as a solution is the following vector field. So it's given by a certain function t, depending on the angles, plus u over 2 divergent of some y. So what is this y? Here, yz is what is basically the z components of this vector field. So y only depends on z. I will explain that. And there is another and a similar story for the anti-holomorphic piece. And there is an expression for psi r, but this is not important what it is. What is important in this is that this t is an arbitrary function of its argument. And that ya, so which is y, z, y, z bar, is a conformal filling vector on the celestial sphere. So you can write the conformal Killing equation for this vector field. I will not. So what I want to tell you here is try to convince you that these symmetries are very rich. And this is what people call, so the fact that t, this function, is arbitrary is what led people to call these symmetries BMS super translations. So I know this is the superstring school, but this super here has nothing to do with that. This super just means the following. It just means that we have an enhancement of symmetry where the 4 global translations of Poincaré, they include in particular these 4 translations, but also so they are enhanced. There are many, many more. There are actually an infinite amount of them because this thing is an arbitrary function of the sphere. So you have an infinite way to generate them to these infinite dimensional super translations. So the super just means that you have an infinite amount of translation on the celestial sphere. So this is actually it was very, very surprising for Bondi, Messner, and Zag when they found this symmetry structure, because what they wanted to find, they wanted to recover the Poincaré group, namely the isometric group of flat spacetime. That would have made sense. But instead, they were stuck with the appearance of an arbitrary function here. And they were really pissed. They said, okay, what is this function? We don't want that. We want this to span just the 4 global translations. So, and they really tried hard to kill this function. They really tried hard by imposing stronger boundary conditions, But what they realized is that as soon as they wanted to kill this function, what they were doing actually, it was to kill all gravitational radiation. So they came to a conclusion, okay, I mean, it seems that if you want to encounter radiation, we have to allow for these symmetries. And then people really didn't know what to do with that. Until in the early 2010, where Andy Strominger and collaborators realized that not only these symmetries have to be there, but that they encode in a very powerful way things that were known from a totally different perspective in quantum field theory, which was known as sub-theorems. And I will tell you about that tomorrow, how these symmetries are actually extremely powerful. And I don't have much time to talk about these conformal killing vectors here because I'm running out of time. But basically, let me just say in one word that if you ask these y's to be globally well defined, you will find the 6 Lorentz transformations, 3 rotations and 3 boosts. But if you relax this assumption, namely, you allow for the y's to be meromorphic functions. So you allow for local singularities. Then you have a similar enhancement of symmetries where the 6 Lorentz transformations, well, as you know, in CFT2 are enhanced to a local version of that, which is the local, which are the local transformations, and which span 2 copies. So y and y bar span 2 copies of the Virasoro algebra, or more precisely the Witt algebra, which is the Virasoro algebra without central extension, because we are at the level of the fields of the vector fields here. And sometimes people call these super rotations. And these were advocated much later by Glenn Barnish and Cédric Troussart in around 2008, I think. So this is a much more general, recent story that is motivated actually from a holographic point of view, and I will come back to that. So let me stop here for today and take your questions.
Okay, let us thank Laura for that.
Hi, I was curious how one could describe